So we'll get started and finish up chapter 4. Okay, I'm going to backtrack a little bit because the place I left off, I didn't realize I need the information from what we did right at the tail end of last meeting to complete the discussion of subsequent slides. So I'm going to back up and pick it up here where we left off. Okay, so we're going to, we're in stoichiometry, these precipitation reactions, double replacements, in which you put two solutions together and the free floating ions interact. And if a cation from one reacts with an anion from the other to form a solid, that's called a precipitate. And that is actually what drives the reaction, the formation of the precipitate. All right, so let me put this equation back up on board and we'll work out this part of it, what precipitate forms and the mass of the precipitate that formed. And then in subsequent slides, ask some more questions about that same reaction. That's why I want to put it up here first. So we got sodium phosphate and lead 2 nitrate. So let's see if I put it right about here. Sodium phosphate, and that's aqueous, and lead 2 nitrate. That's a 2 plus, this is a 1 minus. Go. That yields what? Free ions, free ions, free ions, free ions. This one reacts with that one. This one reacts with that one. And if you look at your chart, you'll find that this one, 2 plus, 3 minus. Like that. That is the solid. And then the other is sodium nitrate. Okay. And that's still in solution. So these sodium, these nitrate ions are spectators. They're just there. If they do anything, all they do is influence the ionic strength of the solution. That's it. So we need to balance this too, don't we? We balanced that in the previous slide. We did. Okay, we need to do that. Okay, so you want to use the budgeting method, or you want me to just slap it up there? Let's use the budgeting method for practice. Right, so we got polyatomics that are the same on both sides, so you can use those as balancing groups. So we're going to have sodium. Let's see, I'm about to run out of space here. Sodium, phosphate. I'm not going to put the charge there. Lead and nitrate. I think that gets everybody. So on this side, we have 3 sodiums, 1 phosphate, 1 lead, and 2 nitrates. Now on this side, we have 1 sodium, 2 phosphates, 3 leads, and 1 nitrate. Usually these double replacement reactions balance really easy. They don't take a couple steps. Very well behaved. Okay, so where do we start? I start at the top. We need 3 sodiums on this side. That gives us 3 nitrates, right? Okay. Phosphates, we need 2 phosphates over here. Oops, wrong place. I just saw the P and automatically decided 2 phosphates over here. That gives us 6 sodiums. Okay. What's next? Lead. We need 3 leads over here. We got 3 over there. We need 3 here. That changes this nitrate to 6. And now we need, notice that these two are balanced. Lead and phosphate are balanced. We won't have to touch those. The sodium and the nitrate need to change now. And if we need 6 nitrates, that means this has to be changed to 6, which gives us 6 nitrates and 6 sodiums. So 6, 2, 3, 6. We're balanced. Okay? That's one way to do it. There are several ways, depending on where you start, where you go at each step. You can balance it any number of ways, but you'll end up with the same product. 2, 3, 1, and 6. So let's clean this up a little bit. Make this one 6. There we go. Now we can do some stoichiometry. Until you have that balanced equation, you can't do it. Okay, what mass of precipitate will form? Well, we got to, what are our reactants first? I haven't put that up there yet. 10 milliliters of 0.3 molar. That one. 10 milliliters of 0.3. Let's see, we'll get all my zeros in there. Molar. We're going to mix that with lead 2 nitrate, 20 milliliters of 0.2 molar. Okay. Now, once you've got your balanced equation and you put the amounts of your reactants in here, if you've got only one reactant identified and amount given, you can assume the other one is in excess. When you give them both of them, one of them is going to run out first. It's guaranteed. If we're tricky and give you a stoichiometric mixture, then they'll both run out exactly the same time, which never happens in reality. Okay, so how do we tell what's what? Well, look at this question. What mass of precipitate will form? Let's focus on the precipitate based on what we have here, and then based on what we have here. How much precipitate will form from this one if that one's in excess? Then how much will form from this one if that one's in excess? And the one that produces the least amount of this product is the limiting one. Okay, so based on the definition of molarity, we should change that to liters. Okay, and that's a good habit to get into, especially since we want to end up with a mass over here. If we're not going for mass, then I could show you another trick, but I'm not going to muddy the waters with that one right now. So let's change that to liters, which would be what? 0.020. Two zeros. Liters. And this one is what? 0.0100 liters. Is that right? 1, 2, 3. Yep. Okay. Now, remember, you can't go anywhere in a balanced equation unless you're moles. You got to change your identity. So how do you find moles from this? Well, it goes back to the identity of molarity. Moles per unit volume. So moles is equal to molarity times volume. That's what we need to do. Multiply the molarity times the volume. Okay, let's see. Let's go ahead and do it for both of them, because we're eventually going to need them both anyway. So 0.01 times 0.3 is what? 0.003. Correct? Moles. Did I do that right? Moves this one a tenth over. Right. But 3 times 1 is 3. It should be right. If I did one wrong, tell me. Don't just sit there and snicker. Okay, this one would be 0.00400. Okay, now we can use a conversion factor to go from one of these, each of these, to that one. So what's the conversion factor? Where do you get it? Or we just waste our time balancing that equation? You get it from the coefficients, right? For every 2 moles of this, you make 1 mole of that. So if we say 0.0030 moles of sodium phosphate, we can convert that by doing, I'm going to leave out the moles for space, but that's what I mean there, moles. So every 2 of these makes 1 of these. Okay, so you just divide that by 2. And that gives you moles of this one that would be formed if all of this is used up. Let's see if I can do this in my head. 2 into that, 0.00150, correct? Moles of lead 2 phosphate. Okay? That's for this one. Now for this one, let's do a little separation here. This one, we want to do the same process with perhaps a different conversion factor as possible. Right, so we want, this is moles of that compound, so we need lead nitrate. And we want to end up with lead 2 phosphate. So the ratio here is again 1 there, but 3 here. So we divide 3 into that. Let's see if I can do that in my head. So 0.003 into that's 1. And then 10 left over is 3 moles of lead phosphate. Lead 2 phosphate. Okay, now you can compare which one makes the least amount. This one, right? So that one runs out first. This one is limiting. This one is excess. Okay? So how do we find the mass? What's the magic number? Anybody ever heard of molar mass? Okay. What's the molar mass of this compound? Because if you got this many moles of it, you got to use the molar mass of that one to find the mass. So we have to add, I need my calculator for this one. 3 leads, which is, where have, oh, here we go. 207.21. 207.21. 3 times that. Let me sleep on me. 207.21 was it? Yeah. We'll add 3 times that. And then add 2 phosphoruses, right? Phosphorus, 30.97. Okay. And then 8 oxygens, 16 apiece. If I did that right, 811.57. So we have this many moles here. Grams per mole. All right. Let's go back to the question. What are we trying to do? We're trying to figure out how much precipitate was formed in this reaction, right? Okay. So let's see. I've already got that number in my calculator. I just need to put this one in there and multiply by it. 0.00133. So I get, how many decimals am I allowed? 3, correct? 1.08 grams of precipitate formed. We identified the precipitate earlier. Oh, we're going to drag this out in nauseating detail. There's the precipitate. Okay. Balanced molecular equation. There we go. Did I do that right? Yeah, they switched them. They put this one in second. So that's right. That's right. That one's right. And that one's right. Okay. Okay. This is the moles. Okay. This is the trick I was going to show you, but decided not to. If you multiply milliliters times the molarity, you get millimoles. And if you divide millimoles by a volume of milliliters, you get molarity. Just prove it to yourself. Moles, millimoles, just use the units. Milliliters, right? What cancels? This is 10 to the minus 3. That's 10 to the minus 3 moles per liter. That's good enough for me. And sometimes it saves a step. In this case, I thought it better to convert to moles since our conversion factor and our calculation was going to need moles anyway. Okay. So we find out what the limiting reactant was, and this is valid. You find out the millimoles here, and you can convert that to moles, right? Milli means 10 to the minus 3. So once you find out, second one, this is the one we want. Once you find out millimoles over here, just change the M to 10 to the minus 3. 1.33 times 10 to the minus 3. You know what this is? Yeah. So that works too. Okay, this one runs out first. That one's excess. Okay, so that means we start with this one, as I did on the board, and convert it to moles here first so we can use the conversion factor. And 108. So I'm good up to that point. The day's young. I still have a chance to screw up. All right, so now what do we want to do? Well, the question now is, what's the concentration of nitrate ions left in solution? Sort of a quick trick question. What happened to the nitrate ions? Well, they didn't participate in the reaction, but they were diluted, right? Because you've only got nitrate from this source, right? From that source. But then you're going to add this volume to it. So now you've got that many moles of nitrate diluted by an extra 10 milliliters of solution. So what we need to do is find out how many moles of nitrate are there, right? Concentration of nitrate ions. And now the answer's down here, but let's go ahead and do it anyway. All right. So, how many moles of nitrate did you have to start with? Well, we had this many moles of the compound, correct? That's just the compound. So if you have that many moles of the compound, how many moles of nitrate do you have? 2 times that. The whole compound. And for each mole of that compound, you have 2 nitrates. So you have actually 0.0040 times 2, 0.080 moles of nitrate ions. Now we're going to dilute those by 20 plus 10, but that's moles. So I've got two choices. Either convert this to millimoles and put those under it. Let's do that. So this is 1, 2, 3. 8 millimoles. Okay, and let's divide that by the new volume. 20 plus 10 is 30 milliliters. Okay, 8 divided by 30. I can't do that. I have to call Spock to do it. 0.267. 0.26. Do I need that many places? I can only have 2, right? No, I can't have another 0 here. There it is right there. There it is right there. What did I say? 267. 267 molar nitrate in the final solution. Okay? That's the concentration of nitrate ions. And to get that, you just have to recognize that nitrate is a spectator. Everything that went in came out on the other end. The only thing that happened was dilution. Got it? I don't want to erase something important, but I do need the space to answer the next question. All right, next question is a little more difficult. What's the concentration of phosphate ions that are left over? Isn't this excess? That means some of those phosphates are left. They remain. And they're going to be diluted by that bond. But we got to find out how many moles are left behind. Okay, how do you do that? Well, how many moles were required? Right? We had, let's see, best way to approach this. We know that we have this many moles of the compound. Okay. So how many moles of phosphate do you start with? Well, it's 1 to 1. 1 phosphate per. So that means you also have this many moles. This many moles of phosphate ions. That's where you start. Now, how many did you use? Well, let's see. If we go back over here, we find that we ended up with this many moles of lead 2 phosphate. So how many moles of phosphate were required? That's the molecule, right? And there are 2 molecules per, 2 phosphates per molecule, correct? So that means you actually used 0.0026. Actually, it goes on out. Rounded, be 67. Moles of phosphate. So that's what was required from this. So we subtract that 0.00267 moles of phosphate. What's left over? Let's see, 3, 6 minus 3, and that's it. That many moles of phosphate remain. So now the concentration is just divide that by the volume. Let's do the same thing that we did before. 3 places. 1, 2, 3. 0.33 divided by 30 milliliters. This is millimoles of phosphate. And be thorough. And then we had 30 milliliters, correct, of solution. So 0.33 divided by 30. I get 1.1 times 10 to the minus 2. 1.1. I'd go further than that. Yeah, I can put another 0. 10 to the minus 2 molar phosphate in solution. That's what's left over. And there it is in standard notation. Okay? That seems like a lot of trouble to find one little tiny number like that. That's what chemistry is all about. When you're presented with mud, you make mud pies. Okay, any questions? Okay. Let's move on to acid-base reactions. Okay. Acid base. Let's see. We're going to have acid base discussion. I think, let me check my 102. I think the second semester goes into more depth. So this is helping me decide how much I want to say about it. Yeah. We'll just give you the bare minimum required to solve problems. What's an acid? What's a base? In this model of the acid base, which we're going to use, the Bronsted-Lowry model, an acid is a proton donor. So when we write, remember back when we were naming acids, you always started with at least one proton. And then you had some anion attached to it, like nitrate. Or you might have chloride attached to it. Or you can have more than one. Like that, sulfate, sulfuric acid. Or even one made out of the phosphate ion. And we were just using phosphoric acid. Okay, those are all acids. They have the ability to donate one of these protons. Let's do another one, just to make a point. Acetic acid. This proton is donatable. Those protons are not. These guys are locked in there, too solid. They will not move. But this one can dissociate in solution, in aqueous solution. And those free protons are what causes the acidity, for lack of a better term, the acidity of the solution, those free protons. Lastly, they're not free, but come back the second semester and I'll tell you why. Proton acceptors are bases. So we typically have hydroxyls of alkaline metals and alkaline earths. So sodium hydroxide is a base, and potassium hydroxide is a base, and calcium hydroxide is a base. Magnesium hydroxide is a base. Just examples. So how do these accept protons? Well, in aqueous solution, they break up. Like that. There you go. So if this is going to break up and produce protons plus nitrates, there you go. There's your proton acceptor as part of that molecule. And what does this give you? Every time. Water. Okay? That's why And these, let's see, that's a weak acid, that's a weak acid. That's a strong, strong, strong. That's a strong, strong, and technically these are strong acids also. Bases. So why do we put this up here as the net ionic equation for an acid-base reaction? It's based upon the proposition that you have, for example, hydrochloric acid. That's how you write hydrochloric acid. And maybe sodium hydroxide, for an example. What happens? Actually, this is a double replacement type of reaction. That one swaps with this one. Pure liquid. And then this one swaps with that one. Okay? So where are the spectators? Well, if these are free ions, you got chloride here and sodium ion there, you got chloride ion and sodium ion there, so those are spectators. They just go out. And you're left with hydrogen ions, hydroxyl ions, yields water. Okay? So for the vast majority of acid-base reactions, the net ionic equation is protons plus hydroxyls yields water. There are exceptions, right? But we're not going to discuss them right now. Okay, let's put it that way. That's too much too soon. What we want to do is use these to identify acid-base reactions and do stoichiometry with them. And that's important because we're going to do a lab using that stoichiometry. Later on, we're going to do an acid-base titration to determine the molar mass of citric acid. So you got that citric acid is one. We're going to titrate it with sodium hydroxide solution and determine how many moles of citric acid we have in that beaker. And we weigh how much we put in there. So what does that give you? You got mass, you got moles, calculate the molar mass. Okay. All right, so where are we going from here? We're going to a video that won't run anymore because it's Flash. Flash is not supported any longer, and I haven't extracted that one from my slide set yet. I need to find a replacement for it first. I think that's why I'm leaving it there. I'll go out on the internet and I'll find something that will substitute. But in the meantime, acid-base reactions. Okay. This is just in green lettering how you do calculations with acid-base reactions. And read that at your leisure. I think it'd make more sense if we just work a problem. I guess we're going to have to talk about it a little bit more. I mentioned a word that I didn't define, titration. Titration is just that. You deliver a measured volume of a solution of known concentration. If you know the concentration and you know the exact volume that's delivered, you can calculate the number of moles of this solution of the solute that is delivered. So, for instance, if we're using exactly 0.100 molar sodium hydroxide, and we deliver so many milliliters of that, say 100 milliliters, right? Then how many moles of sodium hydroxide did we deliver? Well, 100 times 0.1 is 10 millimoles. Or if you need it, 10 times 10 to the minus 3 moles, or 1 times 10 to the minus 2 moles. That's how much we delivered if we put that much into the solution. That's known as the titrate. Now, the substance we're adding it to, in this case, since this is a base, we're adding it to a beaker which has an acid in it. And maybe all we want to do is standardize that acid. We want to know what the concentration of the acid is. So if we put exactly that much in there, then we need to know something about the acid. If the acid is only 1 proton, right, it makes a water and sodium chloride. So we know that if we put this many moles of sodium in, we put, then that's to reach neutrality. In other words, stoichiometric point, which we call the equivalence point. Now all we have to do is get really close to make the calculation. So if we know this was delivered 1 times 10 to the minus 2 moles, that means at the equivalence point, then we know that this is equal to 1 times 10 to the minus 2 moles. Okay? Okay? So if we know that many moles, then suppose we put, oh, I don't know. Suppose this is only 50 milliliters. Right? If we say, all right, if they're equal, 10 millimoles of that neutralized 10 millimoles of that, then 10 millimoles now of HCl divided by 50 millimoles, milliliters of solution, that's equal to 0.2 molar. So that's how we would standardize an unknown solution of hydrochloric acid. When we go in the lab, instead of that, we're going to have, what did I say, citric acid. It's a different relationship because citric acid has 3 protons. Okay? So that means that we need 3 times that to get to this place. Okay, so you need to know the stoichiometry of the reaction in order to apply this titration business. And we'll talk about it more when we get to that lab. Right? I'm just giving you a taste right now. That's the equivalence point. When the moles of acid equals the moles of base. That's the equivalence point. How do you find that? You need some type of instrumentation. If you want to know the exact point, you need to measure the pH as you titrate. So you add an increment and you write that down, say, what's the pH? Right? As we add base, of course, the pH is going to go from acid to base, which means it's going to go from a small value to a larger value. And you plot that, right? Added base. And then this is pH, right? We haven't even defined pH. Any anatomy and phys people in here? Okay, they describe pH to you yet? No. pH is a measurement of acidity. Okay, that's all it is. So if the number is down here, 1, 2, 3, up to maybe 12, then this is more acid. The smaller number is more acid. So as we add base, it's going to go up, right? And for citric acid, I don't know, it's in this neighborhood somewhere. It'll go up like this, and then all of a sudden it'll go like that, and then it'll flatten out. So the added base here, that's the equivalence point. Okay. And you don't need to know this for a test right now. I'm just trying to explain that the equivalence point is an exact position that must be determined from a plot. But you can't do that with every sample, especially if I've done thousands of these titrations. You don't want to have to do that every time, right? So we use a color indicator that changes color very near to that point right here. It might change here, it might change there, but it's very close. In fact, it's close enough to give you excellent results. So you just watch for that change. So that's what we're going to do in the lab. We're going to use phenolphthalein. It goes from clear acidic solution to pink in the basic solution. And right when it makes that change, you want to know the volume of base that you add. That's a titration using an endpoint indicator, right? So the endpoint and the equivalence point are different, but they occur at as close a position in the titration as possible. You want this one to be as close to that one as you possibly can get it. Okay? So that's the best explanation I can give on limited information. Okay, so now we have this titration of sulfuric acid and sodium hydroxide. The question is, how many moles of sodium hydroxide would be required to react with 1 liter of 0.5 molar sulfuric acid to reach the endpoint? All that means is, when are the moles of acid equal to the moles of base? Okay. We could logically reason it out, and some college instructors will do that. But I want to show you the chemistry, which means I need a balanced equation. So if we're going to titrate sulfuric acid with sodium hydroxide, right, there's a sodium hydroxide solution. We're going to titrate it with this acid. Okay? And it's going to make water. What else? It's going to make sodium sulfate. That's a 2- because it's polyatomic ion, which means you need 2 of those because this is only a 1+. But this is still in solution. Right? Sodium sulfate, look it up. Sodium sulfate is soluble. So, as a side note, what's driving this reaction? The formation of liquid water drives that reaction. Okay, now let's balance it. We got 2 sodiums over there, we need 2 over here, correct? All right. So now we have 2 hydrogens and 2 hydroxyls, which means we're making 2 waters. Okay, now we've got a balanced equation. We can explain, based upon what we're given, 1 liter of 0.5 molar sulfuric acid. 1 liter, 0.5 molar sulfuric acid. Okay, how many moles of sulfuric acid is that? The question is, how many moles of sodium hydroxide are required? Okay, so how many moles of sulfuric acid do we have here? Half, right? 0.5 moles of sulfuric acid. So we actually need 1 mole of sodium hydroxide to neutralize a half a mole of sulfuric acid. And the reason for that is the ratio. 1 of these to 2 of those. And the reason for that is it takes 2 of these protons require 2 hydroxyls to make that water. Okay? I could have just said, well, this one's got 2 protons and that one's only got 1 hydroxyl, so it takes twice as much of this as that, which would be true, but it's likely that that statement would just do this in your head and be gone. So that's why I drug it out in that complicated explanation. All right. So that's all we're going to say about acids and bases right now. Let's move on to redox reactions. Now, did I explain redox last time in any detail? Probably, maybe I touched on it. Probably bears repeating. So what is a redox reaction? Where did the redox name come from? It comes from oxidation, reduction, okay. Reaction. Notice we don't call it short. When we shorten that, we don't call it oxred. It just doesn't sound right. Starting a word with a vowel just does hurt your ears. So we just flip it around and call it redox instead. Okay. Combustion reactions are always oxidation reduction reactions. So what's a combustion? It's anything plus oxygen yielding products. That's a combustion reaction, but it's also an oxidation reduction reaction. Always. Other types of reactions that are oxidation reduction reactions. One in which you have a free element on one side. Let's use A here, and then B, C here. Right? So this single replacement reaction will substitute this A. Let's say this A wants to form a cation. It's like a metal. Then it would replace B, correct? So AC plus B. Whenever you have an element on one side, it ends up in a compound on the other. Or an element in the products that used to be in a compound. That's an oxidation reduction reaction also. So what do I mean by oxidation reduction? Well, as a reminder, if I didn't do this already, there's your mnemonic device. Or is that an acronym? Mnemonic device. I'll settle for that. Oxidation is loss of electron. Reduction, you might guess, is gain of electron. Okay? In chemical terms, that's what that means. And they always occur together. In a chemical reaction, you can't have one without the other. Because if that electron is lost from here, where's it going? Right? It doesn't just accumulate. Otherwise, you'd have a static charge. And chemical reactions don't do that. They're always neutral, at least on the macro scale. So you got to have one with the other. Oxidation reduction occur together. This is an example. So this is sodium metal. I hope they don't leave it out there too long because it reacts with moisture in the air. Usually you store sodium under oil just to keep the air away from it. And this is chlorine gas, right? You put them together. I hope they didn't put that whole chunk in there. Is, let me get rid of this. Now, these things that I showed you before, combustion and element becomes a compound, are like rules of thumb. They're to help you identify oxidation reduction reactions quickly. They're not always that way, but if you have those examples, then you know you have an oxidation reduction reaction. But when we put sodium together, metal plus chlorine gas. What does that give us? Well, the product is right here. After it's been cleaned up, I'm sure. Sodium chloride. Okay. So there's an element in a compound. There's another element in a compound. That's oxidation reduction. It's not balanced yet. You need 2 chlorines, right? 2 there. And now we need 2 sodiums. So that's balanced. But what has happened? What do we know about writing compounds? What helps us write ionic compounds is you know the charge. Right? This is type 1 compound. Sodium in a compound is always +1. And in this case, chlorine would be a -1. How did you get there? Because this one has no charge. It's an element. Right? It's always neutral. And this one's neutral. So if this one went from 0 to -1, how did you get there? Well, it gained an electron. Right? We went from here to here by gaining 1 electron per chlorine atom. And we went from here to here by losing 1 electron per sodium. But how many electrons were actually transferred? 2 sodiums, 1 electron each, times 2, equals 2 electrons were lost. In this one, 2 chlorines, 1 electron per chlorine times 2 equals 2 electrons. Right there, there. That's another characteristic of oxidation reduction reactions. The transfer of electrons, oxidation step, reduction step, they always have to have the same number of electrons transferred. That must balance. Okay, so this one is loss. Oxidation is loss. We oxidized sodium. Right there. And here, let's get this out of the way. And here we reduced. Okay? That's that. Let's see, what else are we going to get? Oh, okay. If the rule of thumb doesn't work, well, even if it does, we need a bookkeeping scheme for tracking electron movement. Now, this is simple because it only happens between 2 elements to make a salt product. But some of them get more complicated than that. And some of them actually do not form ions. And you still get transfer of electrons. But so how do you track electrons when there are no ions? You know, you can't tell how they move. So this is our bookkeeping scheme. It's called oxidation state. Okay? This is one of several types of electron tracking techniques. Organic chemists use a different one. So you'll have to take my organic chemistry course to find out. Okay, so these are the rules for determining oxidation state. In other words, it's kind of like charge, but it's not necessarily charge. And if you know the oxidation state of all the atoms in the reactants and products, then you can track where the electrons went. Because maybe the element on this side had an oxidation state of 2+, and on this side it had 2-. So what happened? Well, it gained 4 electrons. 2 of them made it to 0, and then 2 more made it to 2-. Okay? So this is our bookkeeping scheme. Oxidation state of an element is 0. That's an easy one. If an element in its most common form, for instance, all these metals would just be single metals, right? Single atoms, sodium or vanadium or iron, just written like that, their oxidation states are 0. Okay. If we write some of these, let's see, the diatomics, of course, would have to be written this way. But each one of the fluorine atoms is an oxidation state of 0. Even though we know that underneath, they're sharing electrons. So maybe for a while, one is a slightly negative and the other one's slightly positive. Those things go on, but for our bookkeeping scheme, it's 0. Or you might have phosphorus, which generally occurs like that, or sulfur, which occurs like that. Each one of those atoms is 0. It's elemental. Okay. If you have an ion present, then the oxidation state is the charge. Okay. We're starting off with the easy ones first. So sodium chloride together means sodium is +1 and chloride is -1. Those are charged ions. So any ionic solid will give you a mixture of ions that have whole charges. Okay. Oxygen is generally taken as -2, even in covalent compounds. So here it is, it's going to be -2, except if it's in a peroxide. So what's a peroxide? Right? Everybody knows hydrogen peroxide on your medicine shelf, right? You ever look at the bottle? Sometimes they give you the formula. Like that. So what does that mean? Well, it means 2 oxygens are bound together, and then you got a hydrogen here and a hydrogen there. It's a covalent compound. But this together is -2. So each one of these is -1 oxidation state. You don't have to have hydrogens there. You know, this is hydrogen peroxide, but you can have other types of peroxides with different groups. Notice I use an R there because there are no elements up here with just R. This just means some other group. Anytime you have that arrangement, then the oxygens are -1. But any other time, the oxygens are taken as -2. Okay, hydrogen in covalent compounds is usually +1. If it's not an ion, if we can't identify it as an ion in a compound, but it's still there, we take the oxidation state as +1. The only time that hydrogen is -1 is when it's bound to a metal, like this, sodium hydride. I think if you did that extra credit with naming compounds, I think that was one of them. Maybe I can't remember. Anyway, sodium is always +1. Right? So hydrogen has to be -1. There's no other choice. So in those cases, hydrogen is -1. All right, fluorine is always taken as -1. Right here. All the halogens, when we're writing our compounds, we take the halogens in ionic compounds as -1. But even in covalent compounds, this bookkeeping scheme says that fluorine is -1 always. Now, when you get chlorine, bromine, and iodine, and those in mixture with other covalently bound elements, then they can change. So we have to do some examples of those and show you what steps you need to take. You need to take the obvious ones first and then calculate the others. Okay, the sum of the oxidation states is 0 for all compounds. And for polyatomic ions, the oxidation state is the charge of the ion, the sum of the oxidation states. So something like this, NO3 minus, the oxidation states here have to add up to -1. Okay, so let's do that. Oxygen is -2, right? We said that. So how many minuses is that? Total -6, correct? 3 times 2 is 6. least in my universe it is. So if this is -6, how many of those do we need to neutralize? Only 5 of them, right? We want to hold out that negative for the charge on the ion. So we only have to neutralize 5. That means nitrogen has to be +5. So that's how you calculate an unknown. Nitrogen varies all over the place. In fact, if you look at your periodic table, not this one, but any of the others that I've handed out, you'll see lists in each box of different, what look like charges. Like sometimes those are charges, but sometimes they're oxidation states, more often than not. So nitrogen will have a bunch of them. Some of the elements have lots of oxidation states possible. Okay, those are the rules. Now we got to use them. So K2Cr2, let me check the time. 140. 140. Oh, I'm going to run out of time. How much more we've got? We're going to skip that. Already talked about that one. We're gonna skip all the way. We're gonna skip over to balancing equations using the redox method. All you have to do is say, all right, that's -2. This is +1. Calculate what chromium has to do. It's probably a +6 in this one. You do the same thing with polyatomic ions. You just have to hold out enough of those negatives from oxygen and not neutralize them. Don't neutralize them. Keep them because you need them for that. And then what's left over, this is a +4, I bet. Yeah. And manganese, right? That's a 2- times 2 is -4, so this has to be a +4 for manganese. And this one is a covalent compound. So which one do you start with? I start with the halogens. So we're going to take chlorine as -1 in this case. So it means phosphorus has to be +5. And fluorine, of course, is always -1 oxidation state. That means sulfur has to be +4. Okay, so we need to do that one really quick. Okay. One thing I didn't mention. When I said something is being oxidized, what causes that? Well, the other guy that's being reduced. So the one that's reduced is actually the oxidizing agent. The one that's causing the oxidation is the reducing agent. So whatever is being reduced is the reducing agent, is the oxidizing agent for this process, right? It's just converse. We're going to skip this one. I wish I didn't have to. This is an interesting reaction. It's called disproportionation. It looks like you've only got one reactant over here, but actually there are 2 molecules. One of these coppers is reduced and the other one is oxidized. So that gives you this one, which is oxidized, and this one, which is reduced. Disproportionation, look at that. All right, so now let's do oxidation reduction balancing of an equation. So you write the unbalanced equation, zinc plus HCl in solution, so that means it's hydrochloric acid. And then this zinc combines with that chloride, and there should be 2 of them here, in aqueous solution. And then hydrogen gas is produced. I wrote these together, recognizing that this is an ion and that's an ion in solution, the way they wrote it. Okay. Now we want to balance this equation. Right. Well, it's not balanced yet, is it? That's because they wrote the ions separate. I went ahead and balanced it. Come on. Oxidation states, right? This one's 0. This one's -1. This one's +1. This one is 2 pluses, and this one's -1, and this one's 0 because it's an element. Now what do? Well, you got to find out which one's oxidized and which one's reduced, right? Zinc goes from a plus to a 0 to a 2 plus. So I'm going to put that one up here. It had to lose or a loss of 2 electrons per zinc. Right? Which one is, if that one's oxidized, which one's reduced? Well, hydrogen is. The hydrogen goes from gains 1 electron per hydrogen, because we went from a +1 to a 0. And that 0 is for each hydrogen atom. Okay, let's see. Now what do we do? Well, we notice that chlorine remains unchanged. -1, -1. It's kind of like a spectator. Let's draw these in again. Now, we're going to have to balance the electrons first. That's the first thing you do when using this method. Electrons have to be balanced first. So we need two electrons here, so we need 2 electrons here, times 2. How do we get them? Well, there's only 1 hydrogen here, and you end up with 2, so this one has to be doubled, correct? In order to give you 2 electrons. Right, so that one balances that one. Now we look, once you got the electrons balanced, you look at the rest of the equation to see if any other changes have to be made to balance atoms. Right, as long as you hold on to those ratios that we've established, then you can treat it just like we did our budget before. Because some of these reactions are more complicated than that. We're starting off simple. Right? So we got 1 zinc, 2 chlorines, 2 chlorines, 2 hydrogens, 2 hydrogens. That one's balanced. And it's balanced because I did this first. But they're going to do it as a separate step. Oops. So they put a 2 right in here. So this is reality. This is what happens. This is more convenient. Okay. All right. So next thing we want to do is go knock out a lab.